Hello, ladies and gentlemen. This is Friday. Yeah, I can ask tasks. Every Friday we met online. We use these words. I can act tasks, connect the world and the universe. We are so proud that we have I can act already 1 year. Last year, almost exactly the same time, we kick out this I can act tasks. Yeah, we want to have all the students, can hear the latest talk, science talk online. So that time we start this program. So after 1 year, this became one phenomenon in the whole world. A lot of people was get online to hear our talk every Friday. Yeah, so we're proud of that. And this was really, really great program. We thanks for all the speakers. We thanks for all the audience. We thanks for all the technical support for this online talk. It's continuously for such a long time and still, going to, getting into very lovely and uncertain, exciting field. So this week, this is Alex from Beijing. I hope everyone already know me. I'm the host of this I Can X talks, coordinator with with two of my friends, Jagdish and Paul Weiss. Yeah, every week we take turns to get on the stage. So this week is my turn because I definitely it's my choice to host this talk because this talk is really exciting. Professor Martin City, is one of the best professor I ever met in the soft material and the soft machine. His name is Soft-Robots. I listened to his talk once. It was last year summer, online. I was so exciting, because beyond his paper, you hear a lot of backyard stories about his, research. So today we are so happy to have a Professor Martin here. He will give his talk for the latest results. We also will have, Professor Jagdish to be our panelist, ask more questions for the backyard stories of our research. And on the stage to ask some challenging questions to Professor Martin. So without further ado, now let's welcome Professor Martin City. He's the director of Max Planck Institute for Intelligent Systems. This was a new institution. I think it's a new one. You are the first director, founding director of this. And he's now is leading a super larger group and was doing the very, very fantastic job in this, software robots. So, Martin, please.
Oh, thanks very much, Alice, for your kind introduction, and also thanks for inviting me, both also Jagadish. It's my great pleasure to talk today our research on soft-bodied tiny robots. As Alice mentioned, I'm a director at Max Planck Institute right now. I'm also a professor in ETH Zurich and also Koch University. So briefly, before I start my research talk, let me introduce my institute. It was founded in 2011, and we have 2 sites in Stuttgart and also in Tübingen. I'm the first director in Stuttgart, where we do mostly new physical robotic systems, intelligent systems at the small scale, at the large scale, soft materials, rigid materials, haptic systems, and also different medical applications, type of mostly engineering and physical aspects of intelligence. And in the Tübingen site, we have 2 directors famous in machine learning, computer vision, mostly focusing on computational intelligence problems. So as you know, Max Planck Institutes are public funded, the premier basic research institute in Germany and around the world. And they thought robotics and intelligent systems is one of the future scientific topics that the society should invest. And I'm very happy to see that Max Planck Society, as an elite scientist society, is very interested in this field of robotics and intelligent systems. And now our institute has been growing and have many exciting research topics. But in my group, I'm interested in especially mobile robots at the very small scale, which I will talk about today, especially soft ones. But first question we should ask is, why should we make mobile robots small? So especially for medical applications in our case. So the first reason why robots need to get smaller and smaller is because we want to access very tiny, tight regions which could be inside the human body or inside tubes or very small regions of any environment or infrastructure, because many these days it's very hard to access, or even sometimes we can never access into tough, tight regions at the small scale. So in that sense, minimally invasive access, for example, into our vascular system is very important, because when you have any stroke, for example, I hope you never have, or aneurysms, the problem is the doctors need to access there and open the blood clot, or they need to repair the aneurysm by embolization. And current technologies can reach to some areas, but not every area. That's why most of the patients, if they're lucky, they can be saved by if the problem happens in an area where a catheter can access. But if it is in a smaller region, then they need to do surgery, which is very invasive, and then there are a lot of side effects, and even the person might die. So there are not much, unfortunate treatment methodologies and devices these days that we like to now bring such new devices. And the second advantage of being wireless is you can basically implant or leave the robot inside the body, or again, given infrastructure, for a short or long time, because they are wireless. If they have enough power source and they can operate in the given environment, for example, we can leave them in the brain for neural stimulation for a long time. If you are a Parkinson's disease person and you have any neural abnormalities, then what we do is we put our microrobots here, and then they can stimulate wirelessly the neurons so that you can have you can recover from the Parkinson's disease type of some diseases. So again, getting inside small regions, very tough regions, and staying there and doing operations is great. But every new high-impact technology and science comes with a lot of scientific challenges. When you are that small, of course, you will be very limited on power source you could have, how much propulsion force you can apply, how to communicate with outside world or with among robots, computing power, and the functionalities you can put in the robot. It's getting very, very limited and challenging. And the second thing is, if you're too small, how can we visualize and track these robots and control them inside the body is very, very challenging. And finally, also, when you have tiny active devices inside your body, you want to make sure that everything is fully safe, which is, of course, non-trivial problem to make sure that right materials are used, everything is controlled precisely and safely. So all of these issues are very significant technical challenges. The second thing, before that, this is, I've been teaching small-scale robotics since my UC Berkeley times and Carnegie Mellon time as a professor. So finally, I have this textbook written when I came to Max Planck. And if you're interested in learning about small-scale robotics, this is a good resource book to read about how to design, how to actuate, sense, locomote, power these tiny devices. But today, I want to especially focus on soft-bodied tiny robots. And now then, the second question, while you become wireless and small, why should you also be soft? So if you look at especially biological systems in nature, we see that some organisms are fully soft, and some of them, like us, are partially soft. Why do we have softness in our bodies? Because the one first important aspect is, because of softness, we can adapt to environment, and physically we can program our shapes, color, and many properties much in a complex way than a rigid system can do. We can also adapt and change our behavior much easily if you are soft and continuum. The different behaviors you can have is much more drastic and nonlinear than rigid linear systems typically that we have in robotics. And also, because of this diversity of shape, programming, and behavior, you can induce a lot of functionalities. The same arms can be used for swimming or as legs, or also as manipulators for grasping fishes or other objects in the environment. And also, as I mentioned, in medical applications, safety is a big issue. And if you are soft and interact with the patient directly inside the body, a soft body makes sure that you are relatively very, very safe with compared to rigid robots. So then soft robotics now is a very hot, exciting topic in some, maybe since last 10 years. And if you look at, there have been a lot of great progress in designing new soft actuators for these soft robots. So these are some summary of different approaches. You can use temperature, magnetic fields, air or fluid pressure, electrical fields, light, chemicals in the environment, all can create very interesting small-scale or large-scale soft actuation. Even these days, people are using biological cells as actuators for soft devices. So now I'll show you our main interest in these different new soft materials for creating soft actuators and then soft robots. I'll start with first very tiny ones at the cell scale, which are driven by live cells for creating soft, tiny robots. What we do here is we take from a patient their red blood cell from a very small blood sample. We can get millions of red blood cells from a patient. And you can engineer these red blood cells and empty inside and load it with drugs and also magnetic nanoparticles and also other agents you want. So that way, your red blood cell turns into a carrier, which is biological material, but then it's loaded with all the synthetic nanomaterials, also drugs and molecules that we want to use for cancer treatment type of applications. However, red blood cell, as you know, is a passive material. It cannot propel itself. It moves with the blood flow. So to make it a robotic device, what we do here, we coat the surface of the red blood cell with an antibody. Let's say in this case, for example, avidin. And then this specific E. coli bacterium, which is live, has biotin on the surface, which we bioengineer. And that way, the cell membrane of the E. coli bacterium sticks to the red blood cell because of this avidin biotin strong bonding, which is very specific bonding. So that means now we can make micro cell scale robots, which are driven by bacterium, single or sometimes multiple, and the red blood cell is the carrier where we can functionalize with nanomaterials and the drugs. So now let's see it in action. So here you can see that this red blood cell is propelled with the bacterium attached to the surface, but then with the remote magnetic field, because of the magnetic material inside the red blood cell, we can drag it where we want to go inside the body. So that's getting very exciting that we can use live cells, and that way we can steer them where we want to deliver eventually drugs and other things. So the nice thing about red blood cells, as you know, is they are elastic, they are soft, and they can squeeze through very small gaps. Because our microcapillaries in our brain, for example, goes down to even smaller than your red blood cell. And if you look at red blood cell mechanics, they can squeeze through, of course here, because bacteria is also propelling it, through this very small 2-micron gap because of its soft body. So that's why we can have these tiny robots that can go in the circulation of the vascular system without getting stuck even in microcapillaries. So after achieving this kind of navigation capability with the bacterial propulsion, then what we showed in the study is how to show some therapeutic functions. So here what we did is we loaded the red blood cell not only with magnetic nanoparticles, which are iron oxide, also ICG is a basically photothermal agent that if you shine an infrared light from outside, which can penetrate the skin up to several centimeters, that way these ICG molecules absorb the infrared light and get, of course, warmer and warmer up to a temperature where the red blood cell gets neutralized and decomposes, and that way we can fully release the drug inside. In this case, we use doxorubicin, which is a cancer drug, and we basically release the old cancer drug in the right target. The second thing we did here is, because of the increased temperature, we induce hyperthermia. As you know, hyperthermia is around 41 to 45 degrees, depends on the cell type. If you heat up locally any particle in nanomedicine, this is a very popular technique. That way you also kill the cancer cells because of hyperthermia, because of increased temperature. So here we had both hyperthermia-based treatment, but also cancer therapy by chemotherapy of releasing the drug at the same time. And finally, also because of the increased temperature, the attached E. coli bacterium, which is non-pathogenic, was also killed. That way, in the body, we had nothing left over in the sense of potential side effects afterwards. So this is, I could say, the most advanced demonstration at the cell scale, how a soft robot can go to a target, can be steered and guided, and eventually release drugs and do therapeutic functions at the small scale. Another recent development that we published last year in Science Robotics is not only using red blood cells, but also we are started using immune cells of the patients to use them for cancer therapy. So here we took macrophages of a patient, and then we loaded with synthetic magnetic particle, in this case a helical shaped basically body. That way we could drive the macrophage on the surfaces by rolling from outside magnetic actuation. That way we can steer the macrophages to a target cancer region, and then macrophages can penetrate the tissue to reach the cancer, and then we functionalize the macrophages to make sure that they call other immune cells because they are in alerted state. That way we created immunotherapy. That's why we call these robots Immunobots. But the difference from literature is now we can do targeted immune therapy by localizing our macrophages into a target cancer region and actively recruiting the other immune cells to treat or kill the cancer cells. So that's why this is an exciting direction that we are right now applying in real animal experiments at the moment. But today I want to show you bigger milliscale robots a little bit more because they are much more complex and advanced in the sense of soft-body dynamics. And here I'll show you fully synthetic robots made out of synthetic materials, and also I'll show you some of them are made of also biomaterials, like I showed you before in the micron scale cases. So one example of synthetic soft devices we are building recently is using hydrogels and 3D printing them with 2-photon polymerization. These days we can make few micron scale robots 3D printed from polymeric hydrogels with near-infrared light focused by 2-photon systems. And these high-resolution printing systems, if you combine with stimuli-responsive materials like pinipalm in this case, what we have shown here is the spherical or any shape of 3D printed robot can use the stimuli in the environment, which could be temperature change, which could be pH change or calcium ion change, that can induce swelling or shrinking of the size or the volume of the robot that can create shape-adaptable, size-adaptable robots. Why is this important in medical application? Because I mentioned aneurysmas at the beginning. When you have a bleeding in an abnormal way, typically doctors, what they want to do is they want to go and block that vessel so that you don't bleed out and die. So in this case, for example, we can go through these small channels and eventually we can block by controlled stimuli in the environment or from outside to make sure that we can create some soft clogging active devices with these kind of stimuli-responsive materials, is an example. Another example is using proteins as a biomaterial. So what we have been doing is looking at nature, and this squid ring teeth is very interesting biomaterial, which is a protein that is very tough, very strong, because they catch fish with this very strong teeth. We basically take the material, we make it into a solution, and then we can pattern it as a film and cut it with a laser and turn it into robots. In this case, we also load to the protein some fuel, a chemical fuel in this case, and if you put it on the air-water interface, the fuel will diffuse to the water very controlled way because protein structure is very precise, and that way we can make propulsion due to the surfactant diffusion to the water generating surface tension gradient. So this kind of Marangoni propulsion is a great example at the small scale using biomaterials and a fuel to make hours of operation at a very, very high speed. The nice thing about these also proteins is they can heal themselves by room temperature or some local temperature. So here a demonstration that we take the same protein, but in this case we even biologically engineered it. We call it synthetic biology engineering in collaboration with Penn State. So as you see, after cutting and applying a local temperature, in seconds, I mean, this is the healing time, is in second, our material cures and gets the strength of the almost original material. So that way, if there is any mechanical damage to the soft actuator, we can immediately repair it with a local temperature, or just waiting for hours in the room temperature, it will self-heal itself because of its protein structure here, again, using beta sheet these nanocrystals and the dangling chains. This kind of material, when it is mechanically damaged, by diffusion in a very fast time scale, they can reconstruct these dangling chains and then become the very cohesive, very strong material again. So here, more mechanical demonstration of this protein as an actuator. So here we see we use a pneumatic actuation by just making out of this protein this kind of membrane structure. By inflating and deflating, you see that we can create very strong soft actuator, which again, if there's any mechanical damage, we can immediately repair or self-repair repair itself, so it can keep functioning even against mechanical damages. So now another material I want to show you before I get into our main magnetic materials is liquid crystal elastomers have been very interesting for our group and for also a lot of materials people, because they can be programmed in their stiffness, and they are stimuli responsive, and they can be very interesting soft actuators. So our recent work used a liquid crystal gel where we could align the molecules of liquid crystal elastomer, in this case gel, in specific directions, so that underwater, when you shine a laser and create a photothermal heating, we could deform it at a very high speed. So you see this a real-time video for the first time, because underwater, any thermal heating-based actuation is typically very problematic because of very fast heat dissipation in water. So here we use a very low intensity of light, and we engineer the hydrogel here of liquid crystal gel in a way that with small temperature change, we could actuate it with very low power consumption. So that's why it was well recognized and almost getting the Cozzarelli Prize recently. So in that sense, we can use these liquid crystal gels for, in this case, heat-driven, light-driven, basically, actuation underwater. So also, we can take the similar concept of liquid crystal elastomers and again, align the molecules, because these alignments can be done in almost any manner of horizontal, any chiral. As you know, liquid crystal displays use chiral morphology, basically molecular alignment. They call director fields. And by controlling these director fields or alignment of the molecules of liquid crystal, then we can take and put them basically use them as a dielectric elastomer actuator by putting two electrodes on the top and bottom made out of a grease conductive electrodes, like typically done in dielectric elastomer actuators. Now, the difference we have as a novelty here, we use, rather than a typical elastomer, we use liquid crystal elastomer and align the molecules in any direction we already program. And that way, when you apply the electrical field and create this actuation due to the electrostatic pressure, now the elastomer doesn't have isotropic actuation, but has anisotropic actuation programmed by the alignment of the molecules. So because in one direction, this material is very stiff, in the other direction, it's very soft because of molecular alignment. So more complex programming of this, you see here, same monolithic elastomer. We put grease electrodes and then basically align the local molecules in different directions. And when you apply same voltage to the whole surface, you see the different morphological change because of programmed molecular alignment on the liquid crystal elastomer part. So in that sense, LCs are getting very interesting for different soft actuation systems for more complex programming of shape deformation. This is another example at the micron scale. So we can, again, 3D print using two-photon polymerization LC, liquid crystal elastomer structures, in this case ring, for example, but any structure we can print. And nice thing here as a new contribution is we can align the molecules in a channel in a way that when you apply stimulus to this ring fabricated structure with different molecular alignment programmed in different ways, we can induce different shapes by, in this case, swelling, or if you apply temperature, you will get the similar effect. You see that you can induce a change in this shape change, or just increase of the volume isotropically, or much more complex twisting behavior type of shape transformations. So all these things are being enabled because of, again, alignment of the molecules in controlled ways while we do the 3D printing. So, but today I want to spend my time more on our biggest activity, which is using soft magnetic materials for creating tiny soft machines inside the human body. They are inspired by nature, and as you see here, we want to make swimming devices, cilia, and many other devices which are driven externally from magnetic fields. So why magnetic fields are interesting for actuation at the small scale, or also for soft actuation? Because the nice thing about magnetics is it's long range. That means in the body, you can have an MRI these days with even up to 7 Tesla. With a high field, you have no problem and no damage to body. You can have a long-range image of our body with no pain and nothing if the parameters are right. So in that sense, it's directly compatible to medical applications. You can, in these high forces and torques, so for example, if you have a robotic body with magnets inside, with a magnetization of M, if you apply a field, as we know, we can align the robot direction by applying a torque due to the applied field. So that's how a robot will follow and will be guided from outside with the electromagnetic fields. And also, if you apply a magnetic gradient by moving a magnet, for example, then the same magnetic material will be now pulled by this gradient of the magnetic field. That's what we call magnetic force induced by, again, the gradient. So that means if you apply a field or gradient or both, you can have robotic bodies that you can both rotate and align plus pull in the direction you want precisely. And this is very fast actuation and very complex dexterous actuation by programming the magnetic field on the robot body. I'll show you. The only drawback of magnetic actuation is you need to have a magnetic field source or gradient source that typically is possible to arrange in a fixed workspace. For example, you cannot have a flying robot magnetically actuated. But if you have a medical robot in the body, this is not a problem because, again, the workspace of the body is small enough or compact enough that it's easy to generate magnetic field from outside and gradient also from outside. So now let's start playing and designing soft actuators using magnetic materials. So here, our first work, or pioneering work, I could say, in this field was almost 4 years ago now. We made elastomeric sheets with magnetic particles inside, and we asked us the question. So if I have a sheet of elastomer with magnetic particles inside, and I want to create with the same sheet many different deformations by just changing the external magnetic field, we asked the question, what is the magnetic programming of the magnetization along the length of the sheet we should have to achieve these all desired shapes? So this problem we can mathematically formulate because we call them as desired all deformations as kinematic deformations. Then we represent all these magnetizations we need to have and the applied fields from outside that we control. And if you do a Fourier coefficient expansion of all these parameters and do an iterative genetic algorithm-based evolutionary optimization, at the end you find an optimal magnetization profile that will give you all these desired shapes at the same time. So don't forget, we are not talking about one shape, we are talking about hundreds of shapes at the same time achievable with the same elastomeric sheet. So after we find the optimal magnetization, then we fabricated that kind of magnetic programming on the elastic sheet in this way. So first, we made the negative of the elastic sheet and put an elastomer molding. Then with a laser, we cut the elastomer in specific area and filled it with magnetic microparticles, which are very strong, with a composite of elastomer. So these dark regions are only the ones that are magnetic. And then if you use a 3D printed jig and deform this elastic sheet and apply a very strong field, which is easy to generate with high field generators, and then open the jig, you will get this, depends on the morphology of the jig, these different magnetic profile. As you see here, both the direction of the magnetization is different along the sheet's length, and plus the field strength is different. The magnetic control is achieved by the area of the magnetic material. So if you have everything magnetic, they will be all having the same amplitude. But by playing with the area of the magnetic material, at a given length, we get less magnetic material or more magnetic material, so amplitude can be controlled by the material amount, and the direction is controlled by the deformation through the jig that before magnetization. Because at the beginning, particles were not magnetized, they are magnetized after deformation. So this is a patented technology that now we can make very complex, different soft machines or actuators. For example, we can now make a sperm-like undulation of the body. As you might know, when sperms swim, their head is almost fixed, and their body is undulating with an amplitude increasing at the tail tip. So this kind of undulation is not very complex to achieve. And our algorithm computationally found the magnetization along the length of the sheet should be with this kind of profile. And that applied magnetic field should have this kind of phase difference profile. So after we fabricate with the method I showed you, the elastic sheet and spin the magnetic field as we found, you see that we get this undulation where the head is almost fixed and then the tail has increasing amplitude. Now, you can basically build a sperm-like swimming machine, we call robotic sperm here, that is using this kind of magnetic soft material that we program and actuate from outside. That was our first step in this kind of methodology and the concept. And the second, we have been recently improving more complex fabrication techniques where we can even reprogram the magnetic encoding of the material. Can you hear me? Is everything okay? Okay, good. This is a new technique that's called heat-assisted technique, because in the previous one, we could program the magnetic field one time, and then it's been fixed. But in this method, what we can do is we still take the same elastomeric sheet, but now put inside a different...
Informative and impressive talk. I know you.
Songyu, could you please turn on? Okay, yeah, okay, hey, mute,
okay.
Sorry.
Okay, perfect. So you can hear me, right? Great. So now, rather than niobium iron boron microparticles, which are very strong, now we use chromium oxide microparticles, which are also magnetic. But the difference of chromium oxide magnetic particles is if you apply local laser heating, the Curie temperature of this magnetic particle is relatively low, on the order of 100, let's say 70 degrees. That means by local heating, we can fully demagnetize. So because if you take a magnetic particle or material, if you go above the Curie temperature, what will happen is above this Curie temperature, you will basically demagnetize the material. In that sense, basically what we do is first we demagnetize the material by heating locally, then apply external magnetic field so that we can magnetize in a given direction we want, and then we freeze it in the room temperature, because when you go below the Curie temperature, the alignment that you induce will remain. So that way, locally, this is a great thing about this technique, locally you can program any direction you want on the fly just by controlling the local heating and external field. So you can change, of course, the field direction and magnitude that will have different alignment and also magnitude of magnetic fields. So that way, for example, now we can build these soft machines. In this case, we call it a flexural metamaterial. You see that when you apply a field, and depends on this magnetization direction of these all flexural elements, you see that the same structure is deforming in different way. Now we can go and use a local heating and reprogram this part, for example, and now the same machine turns into a different deformation body shape. And for example, we can also reprogram, let's say, other areas. As you see with the same robot now, we can induce very different outputs by just locally reprogramming its magnetic properties. So this kind of technique also can be scalable, because local heating, of course, can be sequential like we did with the laser heating, but also you can do with a mask at the same time parallel heating and programming. And even we can do contact transfer by having a master magnet design, where if you heat everything above Curie temperature and press together and then cool down everything, you will instantaneously program the master magnetic program or the basic design into this elastic sheet with the magnetic chromium oxide particles. So that way, we can basically roll-to-roll manufacture soft machines with this technique with magnetic programming in the near future. So that's very promising for commercial applications. So now let's come back to science. And now, rather than just making a sperm-like robot, now let's try to make more complex new robots that uses this kind of magnetic soft materials. So here, 2 years ago, we had a breakthrough in the sense of having a soft sheet-shaped robot that can have at the same time 7 different locomotion modalities on different media like liquids or air or solid surfaces at the same time with the same robot. So let me show you the motivation first. If you look at nature, there are a lot of soft-bodied organisms like caterpillars, C. elegans, spermatozoids, jellyfishes, which they use the soft-bodied deformation dynamics for ground locomotion, in this case crawling or jumping, or undulating inside fluidic channels, or swimming in fluid underwater. So all these body dynamics is very exciting, and question is, can we have one robot that can achieve all of these behavior at the same time? The answer is yes, and interestingly, that kind of magnetic programming of such a robot is not that complicated. Of course, after a lot of computational and also experimental trials, we figured out if you take the elastic sheet with magnetic particles, and now we make everything magnetic, because we don't need to change the amplitude of the magnetization, just the orientation, we discovered that just making this kind of a waveform, which is basically a sine or cosine waveform, with the changing orientation of the magnetization, which can be easily generated by the jig idea, the first method, so that you, for example, first make your particle composite with elastomer, which is in this case a silicon rubber, and we do one-to-one mixing of them. And then at the beginning, the particles are not magnetized again. We wrap it around, in this case, a cylindrical rod, then apply the high 1.8 Tesla field, and the particles are then aligned in the direction of the strong field. Then again, when you open the elastic sheet, because this is just a jig, then you get this kind of profile, and if you wrap this thing multiple times, you can get this wave multiple times. So basically, you control this wave morphology, and then make the material hydrophobic, so water repellent, with some surface roughness on purpose to induce interesting dynamics. And this is a robot which is only millimeter scale and can be even much smaller. So what we did here, we created an electromagnetic system which can induce controlled 3D magnetic fields in a given workspace, which is large enough. And if you don't apply any field, the sheet is flat as it's opened because it's a sine wave that everything adds up to 0, so total magnetization of the robot is 0. But when you apply a small magnetic field in a given direction or another direction, now you can induce a sine wave or a cosine wave deformation, and when the robot deforms, the total magnetization is non-zero. You can also go higher amplitude of the external field, and again, in a different direction, now you can make a loop shape or a V shape, depends again on the magnitude and the direction of the applied external field. So these are our basic shape modes with this kind of waveform magnetization. And the second is because of total magnetization being non-zero, now we can also apply a body torque so that we can also rotate this robot from outside. So now, if we use these shape modes and the external rotation, now we can roll on a surface like a basically wheel, and we can go on the water surface and undulate it like a basically undulating sperm. And then underwater, we can go to the mode of a jellyfish for swimming underwater. So these are all slowed down, and everything is happening with the same robot. What is changing is only external magnetic field. So you see that we can climb on the water meniscus because of shape deformation, and we can walk like a caterpillar. And then when we have an obstacle, we can also jump like a caterpillar. All these actuations are really fast, and this is the walking gait like a caterpillar. We call it 2-anchor crawling on a solid surface. Also with the soft body, like C. elegans was in the channel before in the video, now the same robot in a channel can also propel with the body undulations. So all this behavior is enabled from external magnetic field control. Now we can try to use it for medical applications. So we put the same robot now in a chicken tissue incision. You see that we are swimming like a jellyfish, and now we are imaging it with ultrasound because, of course, inside the body we cannot use a camera. So you see that the same robot can turn into a loop and do the rolling locomotion or jellyfish locomotion, all inside biological tissue media. So that's why these robots are now being designed for a specific medical application I'll show you at the end. But another thing is, besides all these locomotion modalities, with a soft body, you can also use, like an octopus using its arm for manipulation. Now you can use your body shape change to manipulate objects in the environment. So I can grab now this object with the body shape change, roll and transport it and release it by just using, again, shape control. So we can do more advanced version by making a small pocket and put a drug inside the robot and can do all the locomotion as before. And with a specific shape change from outside, we can also eject this pocket of drug into the right target location when we want. So all these things are enabled by shape control. So that was a nice development. And also recently, we combined these magnetic soft composites with now liquid crystal elastomers I showed you before. Now we can make much more complex that can adapt to environmental stimuli, and in this case, a temperature change. So the same temperature change idea, for example, we can take the same liquid crystal elastomer with magnetic particles, and if you have a hot needle, you see that because of programming of the liquid crystal, it can wrap around and grasp the hot needle. If you don't do that, it will not grasp it. So you see that we can combine the crystal elastomers with magnetic actuation together for new ideas. Okay, so now let's go back to magnetic soft composites. Now we want to do much more complex robotic mimicry. In this case, we look at a jellyfish animal, and this is a robot for the first time mimicking the same propulsion and the same morphology with a biological organism at the small scale. I've been working on bioinspiration for 20 years. I could say this is the first time this robot is mimicking exactly a biological organism with the same morphology, same dynamics, same fluidics, and everything, physics same. So let me show you a little bit details how that happens. We first look at the morphology of a baby jellyfish. By the way, jellyfishes are amazingly important in oceans for biomixing and many other functions. You see their morphology where they have these lappets arms with specific morphology and size scale, which we synthetically created with our composite elastomer here, which is the yellow part, which we programmed in this waveform. And we put a bubble for buoyancy because our robot is heavier than the biological jellyfish. And then we designed these, at the end, the passive elements, which have a directional stiffness here. When the arms go down, let me show you here, they have a much large area because it's stiff, but when it goes backward, then it becomes very soft at the end, and then it can basically change the morphology significantly. You see here, so they are rigid when it's coming down, and when it's going the other way, it's very soft at this joint, and that way there's an asymmetric body undulation or deformation that's very essential for propulsion. So now if you do this asymmetric, as you see the motion of the arms of the synthetic jellyfish robot, and look at these fluidic dye, you can see how the propulsion happens. This is exactly the one happens in the animal. But now the nice thing with the robotic jellyfish, we can change the way how fast we go down, how slow we go up, and we can wait in between for gliding in between, and we can change the amplitude of this arms down and up. So we can play with a lot of variables in the body deformation to create different propulsion behavior, which is now possible robotically. So why is this interesting? Because in the small organisms and also robots, it's not only about going fast in the sense of locomotion, but also there are other important factors, how much energy you consume here. So we call it cost of transport. For example, when you go really optimal way, you have a very small energy consumption. If you go very fast, you consume more energy, unfortunately. So, but the change of the body, deformation speed, and the amplitude is important for other functions. For example, jellyfishes also need to predate, means need to collect objects, basically food in the environment, under their umbrella where they have their basically mouth. So that's why the collection of the objects are different in different body deformations. And also when you collect them, you want to retain them to be able to eat them. And that depends also on the undulation. For example, if you do small undulation, you can keep the food under your mouth for a long time so you can eat them in a long duration. With all these understandings, which are all controlled by the body deformation amplitude and the frequency, now we can synthetically collect objects and transport them without mechanically touching. This robot is never mechanically grasping this object. It's all grasped because of fluid dynamics of the body deformation. So you see that different object shapes and complexities can be trapped. This could be drug or this could be any object. You can transport it like the baby jellyfish does for eating food. We can use it now robotically for manipulating objects in the environment for the first time. Now, we also made a new version, which was received the best paper award recently, is having also fins in between, because some baby jellyfishes also have such fins. And this design is important because of some medical functions. This robot can also do the previous trapping of objects politically, but the difference is because of the fin between the magnetic arms, it can block the channels basically in a controlled way. So we can basically make embolization if there's an abnormal bleeding, we can basically stop bleeding by closing a vessel. Or if you don't want to have a baby, we can close the fallopian tube of a woman or a man, and that way we can basically prevent them to have a baby. But when they want to have a baby again, the robot can open the channel or tube, fallopian tube, and then and sperms and eggs can get together. So in that sense, we can do basically clogging of the vessels in a controlled way because of this jellyfish robot. So another recent development, and this has a complexity, is besides jellyfishes, as I showed you at the beginning, we are very interested in cilia in our body. If you look at the cilia, which help for our respiration system, lungs, and also your brain fluid is moved because of the cilia, has this coordinated waveform that propels and pumps the fluid like a micro pump inside the body. So this was a recent publication. Let me show you a little bit of information here. So each cilium first needs to be designed in a way like the jellyfish arms were doing this asymmetric bending. In this case, the bending is much different. So the cilium needs to go left and then right. So we call recovery stroke and power stroke like jellyfish case. And the important thing here at this small scale, if you have a symmetric motion, you will have no pumping, no fluid transportation. So that's why you need to have this asymmetric, left and right should be asymmetric, and depends on how different these trajectories are. This sweeping area, larger it would be, you will pump for more fluid. That's why we maximize first this area by magnetic design of each cilium with the specific program that we can fabricate, and that way we maximize this area. So you see here, for example, after optimization, we can basically move this one cilium right in a different way and left in a different way. If you look at their deformations, is not symmetric left and right, and that way we can create a relatively large sweeping area for one cilium. Now we need to make array of them, and when you make array of these cilia, of course the spacing is important, and also more importantly, the phase difference among the cilium is very important. And if you look at, for example, in this case, when you do optimization by changing the phase difference, if you have a symmetric one, the motion of the fluid versus when you create a phase difference in a coordinated way, you see that the pumping of the fluid is nonlinearly changing, and it's getting even better rather than a symmetric one in a specific negative phase difference. And of course, distance is also smaller, is better for more pumping. And again, these are what they call antiplectic, and this is synchronized, means all the cilia are doing the same motion. There is some pumping because we create this asymmetric sweeping area still. However, when we have the optimization of the phase difference, that means coordination among each cilium, neighbor cilium, we get the best pumping. That's what we call antiplectic. You see the particle is transported at the same time much further away. So that's why, for the first time, we have shown the importance of the coordination among synthetic and biological cilia arrays for pumping fluids and transporting objects efficiently. And by that, now we can create wireless medical devices that can basically pump fluid in the body wirelessly. So this is all done from outside. Each cilium magnetically designed in a different way. They have the same input of magnetic field which is spinning around, but because they are designed differently, they deform at different times. So that's the important design aspect. That way we can create this coordinated wave behavior. And as you see, we can transport objects and fluids inside the body. If you have a damage of your biological cilia, we can now make synthetic cilia for pumping brain fluids or lungs still function as normally. So another by inspiration recently we have had, which will be published soon, is looking at now a larval fish where we look at the body undulation of a fish. This is a zebrafish, a very small one again. You see that these are at very high frequency. We are talking about in 1 second, the body undulates in a baby zebrafish around 80 and 100 times. And this is slowed down video, high-speed video. And if you look at the trajectory or the deformation of the body, is very important here. And to understand at given frequency how they deform and what will be the optimal deformation, we made the synthetic magnetic robot with a magnetic head. In this case, the body, the tail is passive, not magnetically designed, but we made these discrete joints or cavities that induce a different stiffness distribution. So when you create an oscillation at the head, we can undulate the tail in this case because of this oscillation, and you see that we can create exactly the same body deformation like the biological zebrafish, and understand now how much energy is consumed during propulsion at a given frequency. And there are a lot of details, if you're interested, that we have discovered that the fish needs to tune its body stiffness distribution. They do actively because of their active material, so that at different frequencies, they have different deformation to minimize energy consumption. And that's possible to do now synthetically with this kind of design. And we can tune this by the distribution of the stiffness by designing these geometric cavities. So these are all becoming possible now thanks to these magnetic soft materials. So before finishing up, I want to now show you more devices that we like to develop for medical applications using these magnetic elastomeric actuators. So this is very recent work and even not published yet. For example, we are trying to get inside the body now into complex regions, because now we can even have new complex locomotion modality. This robot was helically moving inside the channel of a cylindrical cavity in your ear. And then when it comes into a flat cavity, it goes to another undulatory mode, so that we can use all these different locomotion modalities to go inside bigger cavities, smaller cavities, tubings, and many different regions, because our body has so much complex morphology, so that the same robot can go all in these areas with the different body dynamics controlled from outside. So indeed, the most recent work that will be published in a few weeks is we went ahead with the manufacturing technology to the most complicated level. And in this case, we manually assembled, using some jig ideas as before, different parts, all different colors here, correspond to different materials of a soft robot. So yellow parts are passive material, let's say the purple ones or the gray ones are magnetic composite, and they are bonded in face bonding or edge bonding in specific ways, so that we can have different deformation modalities and complexities induced in the 3D morphology of the robot. So now with this kind of morphological manufacturing technique, which is with multi-materials, we can now make much complex medical devices. So this is a medical anchoring device where when you don't apply any field, the device is fixed because of elastic stored energy onto the channel of the vessel. As you see, there's a very high flow here, which is resembling the blood flow, very high speed. But because of the material design and different materials in this kind of design of the robot or soft machine, with a simple input from outside, with a uniform field, it can contract. And that way we can move it inside to the right or even left, because we can also pull with a magnet the right position so that we can, for example, anchor it into the right place. So why is this interesting medically? Because we can also put stem cells on the surface of this anchoring device, because we can assemble any material basically to the surface or to this device because of assembly technique we developed. And then these stem cells, if you have any tissue degeneration problem, then we can basically anchor this device into the right region in the vascular system and cure and treat this tissue damage degeneration by the stem cell therapy in a local, precise way for the first time. So that's why these kind of devices are now becoming possible thanks to these advanced manufacturing techniques and soft magnetic materials. Another exciting device for us is making a peristaltic pump. As you know, peristaltic pumps are famous at the large scale for fluidic pumping and object transport. But at the small scale, this is a 1 millimeter diameter device, which is wirelessly actuated because of each ring is manufactured by our assembly technique, and each ring has this specific phase difference, like 10-degree difference among each other, which we design. That means when you apply a rotating field, you see that peristaltic wave can be formed for the first time, like our intestines or different organs have peristalsis. That way we can transport objects and create fluidic or object transport also using peristaltic pumps for different medical applications. This is for the first time at the scale as it became possible with this new materials and external magnetic actuation. So another exciting device is a very soft capsule which we design again with this complex assembly technique, which has an opening, and we put a drug inside first by injection, and then we can roll this device inside the body because it's only 500 micron size, these spherical soft capsules, and actively we can on demand deliver the drug exactly where we want. Of course, we can have only one, or you can have multiple of these devices that can roll around, in this case, with the same magnetic field they can go. And when we want, as you see on demand, we can inject the drug at the right place for local drug delivery applications. All these things are now becoming possible for different medical use. So the very final one, again, this will be published very soon, is even we took the same concept and scaled down to cell scale soft machines, because all the previous machines I showed you were few millimeter scale or hundreds of micron scale. But now this machine is tens of micron scale, and the trick here is we make these magnetic particles where we use 3D printing of hydrogels to combine between these particles, and each particle has different magnetic alignment which we can precisely control during the 3D printing, and then we can print basically a robot, soft robot now, with a programmed particle. And again, here, rather than random lot of particles, we have a more specific small number of particles that we precisely control, and then we can make a walking machine or a wave machine that we can trap cells. We can do many different biomedical applications now with these very tiny, also soft machines becoming possible. So to wrap up or finish here, I try to show you different small-scale soft-body robots from pill size almost or millimeter scale to cell scale. I try to show you that we can program their shapes, and even we can reprogram their shapes. They can adapt to different environments, and they can reconfigure. They can even be made out of self-healing materials. They can have functions for locomotion, but also manipulation and other drug delivery type of things. And then I showed you different manufacturing techniques, but even I showed you that we can these days make three-dimensional machines out of multi-materials with advanced fabrication tools. And I showed you that there are promising wireless medical device applications coming up for commercialization, but also high-impact use for improving or even radically improving our healthcare system for medical devices. So of course, these are still very new developments, and there's many things to do next as a near future work. For example, one area we are currently working on is automating the design of these soft machines, because most of these machines, we designed them creatively, but it was mostly human design. We want to now develop evolutionary and other numerical design methods that will automatically generate different soft machines for a desired function we want. And the second thing is controlling these machines. I showed you all these devices were remotely controlled now. So when we do automatic control, then that means you need to do feedback control, and there are very complex dynamics. Indeed, we are using machine learning techniques these days to make these complex thought machines to be able to control it. Then I showed you many different medical functions, and now we are collaborating, and also myself, I'm in a medical school now as a professor, so we are trying to make real clinical applications so that we can really enable new medical devices that will cure diseases that are not curable at the moment, or make it less invasive for patients, or also doctors, also more helpful to doctors. So these are ongoing clinical application collaborations. And finally, of course, all of the results I showed you so far were mostly done in not live animals. So we are currently developing animal experiments where we can use medical imaging inside animals to put our small machines and make sure that they can still do the same functions without killing the animals or patients, and they are safe and they are functional in a complex environment of the human body or animal body, which has many interesting challenges that we are working on these days. So behind this all research, of course, there is an amazing team of researchers I'm very proud of, with backgrounds in engineering, materials, all different types of sciences like biology, physics, chemistry, even computer science, even medical doctors we have in the team. So many of them are now around the world as faculty or in industry. And currently, we have many of these people still around as postdocs or students. But more importantly, we have many visitors from China and other countries. And also, all this kind of very interdisciplinary research requires a lot of collaboration. So we have a lot of collaborations around the world. So if you have an interest to collaborate in any of the topics, please contact me, and we'd be very happy to explore any collaboration ideas. By this, I'd like to thank you for your attention, and any questions and discussions would be great to have now. Thank you.
Okay, great. Really, really great talk. I'm one who was waiting here to be your partner, to be your collaborator. Okay, today we really have a lot of people online and many, many questions. So I choose a few of them. During the panel discussion, I also will ask you some of them. Okay. Yeah, the first question is from Xu from Hangzhou. It says fantastic talk, Professor Martin. Thank you very much. Which of the robots will go to market first in your mind?
Oh, that's a tough question. We are looking at different ones, but what I could say is first, we'd like to commercialize the milli-scale ones, which are relatively bigger, and they are typically in the bladder and GI tract, and also bile duct region, which is safer and easier to commercialize. We have products, devices for vascular system and brain and cardiovascular system, like heart, but then they need much more safety approvals for FDA and other things. That will take a bit more time. So in that sense, I would say anything GI tract, urinary tract, and abdominal areas that is less risky will be our first commercialization medical devices. But we haven't fixed which one will be. So we will create a startup soon, and we are currently exploring. But I would say this is a platform technology. We will not focus on a commercialization of one device. We have a platform technology that we can implement many different medical devices with the same technology by just different customization and different optimization. In that sense, this is a very great platform for many diverse applications with the same company and same platform technology.
That's really, really good. I think it's like the origami one, right? The magnetic program one. That can be tons of that. Yeah, different robots and different applications. Super. Yeah. So next question is Lily from Singapore NTU. Very impressive work for the magnetic control. It has a big problem for the distance and the depth. Also, it is hard to localize when it implanted in the body. How can you overcome this?
Yeah, sure. First of all, these soft devices are designed in a way that they need really small magnetic fields. So if you look at the fields we apply, they are on the order of tens of millitesla. So an MRI is being tested like few Tesla or even over 7 Tesla. So these magnetic fields can be really generated from outside, and the distances, of course, definitely you're right that they will exponentially, you will decay the external fields to the patient's body. But because since they need so small fields, we can still operate inside the deep regions of the body with no problem, with the right medical magnetic device outside. So that's part one. The second, in the sense of definitely tracking these devices, we are currently combining the magnetic actuation with different imaging modalities like ultrasound for milliscale devices. Works great. You can do photoacoustic imaging. If you are not so deep, but few centimeters down the skin, we can track with photoacoustic imaging in 3D at very high speed these robots with no problem. And then X-ray fluoroscopy is another modality we are using for specific medical applications. Doctors have specific imaging modalities they prefer. In GI tract, for example, and also even brain, fluoroscopy is a very common imaging modality. And then we also have MRI in our group, so we use MRI for much smaller devices like hundreds of micron scale devices. Then we use MRI and also PET imaging. So we are looking at all different imaging modalities to track the robot, also track the environment. Because of safety issues, you need to make sure that you know where the robot is and also where the environment is, because it's dynamically moving. And as you say, also control, feedback control is very important here, which we are, again, developing currently with both, let's say, model-based control techniques, but also learning-based control techniques to make sure that we can precisely move our robots in a safe way and in a functional way inside the body, which is very complex.
Okay, thank you Sue, for such a very nice answer, because many students asking for this. Yeah. So, okay,
Sure.
The next question is Professor McGinn. Nice work. I just wonder, if we use in the body, can we see these robots? How can we see them in the real time?
Sure, sure.
Related with the last one.
Exactly. Yeah, as you say, we can. Fortunately, we don't have any more a camera that we can see nice, fast images and in a very clear way. So that's why ultrasound images. I showed you some inside the chicken. You saw it's very noisy. And it's definitely a little bit more complicated. But the nice thing is, if it is miniscale robot, ultrasound and photoacoustic imaging, they can get very high-speed images with some noise, but it's good enough for, or X-ray fluoroscopy also is, the problem with X-ray fluoroscopy is two-dimensional, so that's the problem. So 3D fast imaging, ultrasound and photoacoustic imaging are the best. MRI is the best in the sense of resolution, but the speed is low. So in that sense, the idea here is depends on the specific medical application. You need to choose, and also depends on the size of the robot. Then you need to choose the right imaging modality to see it, and hopefully as fast as possible. But definitely we have in my lab every imaging modality. I can say that most of the applications, there's always one imaging modality works great. But there is no one imaging system works for everything. So you need to choose the right one for each application robot size separately.
Yeah, that's why we do research.
Exactly.
Okay.
That's why there's nothing easy answer, not easy.
The next question is from Xiamen University, Wu Dezhi. Is that complex to construct the magnet generator, and what's the maximum, strength? Yeah.
Yeah. So magnetic field generation these days can be done in two main ways. One is electromagnets, which are the most precise way to induce complex electromagnetic field generation and gradient generation, which we typically do. But then, as you mentioned, the magnitude of the field you can generate will be limited by the coil size and also the distance, as the first question asked. So that's why electromagnets are great if you need low field amplitudes, like tens of millitesla, in some distance. So which is the most precise way. So then the second way is using permanent magnets from outside. So we are developing permanent magnet arrays, not only single magnet, which is the most crude way, but that's still good for some simple applications. So we can design complex permanent magnet arrays where we can program exact magnitude in a given distance. And we can also move the magnets so that we can also create dynamic magnetic fields. So both permanent magnet-based designs and electromagnetic designs work great. Again, depends on the distance of the robot, the field required, in the sense of maximum. So maximum, I can tell you, we are operating right now is 150 millitesla is maximum, and we typically use for those applications what they call Holbach arrays, which are permanent magnet arrays, which are very strong. And then the nice thing is they are permanent magnets are great they don't need any cooling because they are just magnets. The electromagnets are great, but then the drawback is when you go high fields, that's why there's a limit of field for electromagnets, because heating of the coils is a problem. That's why MRI is so expensive, because it needs to be cooled with liquid hydrogen or helium. So that's why the cost is indeed coming from the superconducting system of the cooling system, and also, of course, the electromagnet itself. But yeah, I mean, the electromagnets are great until some strength. Permanent magnets are better for higher strengths, but then they cannot be turned off. So that's why the magnetic field is always on. And so each of them has pros and cons that we look. And in that sense, in our lab, I think we have 10, 15 systems designed customly for different applications using electromagnets or permanent magnets. So that's why there is no one system, again, in magnetic actuation that works for everything.
Okay, so I have to mention this question was from Shenzhen. Yeah, as a her name is Xiaoxia, so I have to mention here. Yeah, okay, that's a very active student. The last question was from Wanji from Peking University. I'm interested in the laser heating system magnetization. Here, I'm curious about the precision of the programming. Yeah, by such method, well, that the heat conductor inside the materials cause the whole materials or can be localized. Yeah.
That's a great question. That depends on the laser heating spot size and the depth. Of course, to have high resolution laterally, you need to make a small spot. That means you will go only small depth. So typical laser method is great for surface magnetic programming. We cannot go deeper, otherwise, I mean, it's not easy to focus laser light and local heating. We have some different ideas for different volumetric patterning, but for typical laser beam-based one, the lateral resolution is typically around 50 micron is possible. Depends on your spot size and then also the depth you need. So the Z is, again, is better resolution, but typically on the surface. So in that sense, yeah, that's good enough technique for our Milli devices. But when you go very, very small, we need much smaller laser spot and heating. That, again, can be improved by optimization of the laser spot size and the intensity and the type of the laser. Because we need around 170 degrees, so that's, as long as you generate that heat locally in a much smaller spot size, then of course your resolution will go higher. But I would say eventually the eventual limit is around 10 micron or tens of micron, because of magnetic particles there is already 2 to 5 microns, so you cannot go too small. So that's our limit there. But right now, with even 50 micron, we already make a lot of machines that are exciting enough. And 10 micron, again, if you push the resolution, that's maybe possible.
Yes. Many cells was really larger than that, so you can control a lot of things. Okay, yeah, that's really great. We also have many questions, but we need to, moving forward, because many of our guests was waiting on the, in the meeting room. Professor Jagdish, okay, turn on your camera, and Dr. Song Yu, are you ready? Yeah, okay, yeah. Let's welcome all our friends here. And today is we're going to have this panel discussion for the soft robots. I think now, Professor Jagdish. Yeah, so you are longtime friends with Professor Martin. So yeah, you must have known him a lot of stories why he can be so excellent, cover everything. Yeah, please.
No, I think, thank you, Alice. And Metin is a very enthusiastic and energetic person, and also friendly and open-minded person. I think that's what really makes him to be able to work with anybody and everybody. And of course, he's a very smart guy as well, as I've known him for about 20 years or so. And so I will ask a question to Metin. Metin, when your technical question about how do you deal with the blood-brain barrier when you're really sending robots into your, Parkinson's disease curing, activation and things like that sort of.
Yeah, I mean, that's a great question. That any robot in the body has a lot of barriers to pass through. As you mentioned, if you're in the vascular system and if you want to reach inside the brain, eventually, if you also go through the vascular system, you need to pass through the barrier. So for that specific question, let me tell you, the answer is Of course, if you're micron scale, it's very hard to pass. As you know, to pass through the blood-brain barrier normally, without any synthetic actuation, if you're less than 40 nanometer, or nanoparticles, basically, or molecules can pass through it. However, if you have bigger molecules like drugs for brain cancer and other, or particles like our neurostimulation robots are bigger, then what people are doing these days, which are really great established techniques these days, is you can take microbubbles, and we also, by the way, use a lot of ultrasonic actuation I didn't have time to show. And if you oscillate these microbubbles in the blood, next to the blood vessels in the brain, the pores open because of the high shear forces. And then you can basically put in much bigger, up to a few microns of size of objects through the inside the brain. So that's one technique these days being used for drug delivery to brain for brain cancer and some other gene therapy applications. So that's, I would say, one way. The second thing is we go to brain not only through vascular system, but we also go through spinal cord fluid. So we inject it through the spine and then go through the ventricles rather than through the vascular system. Then we can reach the deep region of the brain without worrying about blood-brain barrier, because there's less barrier in the ventricles than the blood-brain barrier in the vascular system. So that's one example, but there are a lot of barriers in the intestines and in many areas in endothelial cells. If you want to go through the tumor, inside the tumor, there is a barrier of course, other tissue cells rather than on the blood-brain barrier. So for all of these barriers, we have specific designs of chemical ways or biological ways or mechanical force-based openings. But as you say, that's a great topic to take care while you design your robot and the system at the beginning correctly. Otherwise, you will not pass through them if you don't understand these barriers. So that's why we spend a lot of time on understanding these old barriers. Another big barrier we have is immune attack. I mean, as anything goes inside the body, immune cells go and attack them. That's why we choose our robot materials very carefully. That's why we are using more and more patients' own biomaterials as the robot material. That way, the immune cells know them and they don't attack them. So otherwise, both you can create toxicity in the body or immune shock even. That way, you might even kill the person just because of immune reaction. So as you know, also in vaccines, that's the same problem. So all these allergies or reactions in the human body is another big issue besides the barriers that we are currently spending a lot of time in optimization of the materials. Plus, there's a lot of dynamics. It's not only about material. Our immune system is so intelligent and adaptive. We basically learn, because at the end also we want our robots to be not fully hiding, because if they are fully hiding, they will be never cleaned from the body. So we just design them in a way that they are hiding from the immune system for only a few days during the operation, and after operation is over, we want the immune cells to find them and then even remove them from the body. So these are all very good questions to deal with to make sure that they can work in real immuno environment at the end. That's a great point.
Thank you.
So, yeah, Sonia, are you ready? I'll challenge you.
Yeah. Okay, yeah.
Okay, Lee.
Okay, hello, Professor Siki. Yeah, thank you for your very impressive and very informative talk. Actually, I want a very general question. I know you graduated and got your PhD degree from Tokyo University, and then you went to US and worked for several years, and then you moved back to Europe. You have pretty rich experience over different culture and different academic environment. Actually, our PhDs or postdocs, we also need to make a choice. So do you have some or some experience about how can we find a suitable position among different culture difference? So thank you.
Yeah, that's a good point. Indeed, I have this unique experience of being in different countries and cultures, very drastically different, like Japan and then the US and then now Europe and Turkey originally. So, you know, the interesting thing, like everything in nature and physics, is there is no optimal one system. So every system has strengths and weaknesses, US, Europe, and Asia. They have great strengths in specific aspects and great weaknesses also in specific aspects, culturally, also academically. So in that sense, you know, depends on your career stage. Optimality can change, and also it's personal dependent thing. I mean, because don't forget the professional choices are, of course, one is academic decision, but second is also personal decision. So how culturally you match to the given environment also is very important. And because the important thing here is how to be happy both from your job and also your personal life. That's what I care, because just being happy is always not good. Especially when you get in my ages, you figure out and go back and look, So, and honestly, all these human relations are also very important to be even successful and happy anyway. So in that regard, few experiences I can share is one, if you're a junior faculty, US system is the best still, because Europe and even Asia has a lot of age bias, and really reaching to the best students and best environment, and nobody caring about your nationality, your age, gender, other things, is still, US has been very advantageous if you go into top schools in US. So that's why if you are a new faculty going to US, you can establish yourself faster and much easier than Europe and Asia. Europe is the best long-term, in the sense of culture, in the sense of academic culture and lifestyle. So in that sense, if you see the pattern that a lot of faculty in the US, when they get older at some point, especially if they have any connection to Europe, many of them, not all of course, come to Europe. So that's also, I can say, is a common thing you can observe. Of course, in Europe, not everywhere is ideal, because in Europe the language barrier and cultural barrier is bigger than US, much bigger. So that's why, like Switzerland, Germany, UK, and some countries are easier for foreigners, and some are harder. Asia has been changing and getting better and better and exciting. I mean, Japan in my time was so conservative, hierarchical, let's say. Now they are changing and they are getting much open to, also assistant professorship ideas, and much more open-minded. I mean, China is so different. I mean, each of them are hard to, define. But basically, what I would say is, look at your personal development and see in any of these things you start, and then eventually you can also move on to different ones. It's very competitive. That's a reality, to get any top job in any of these continents independently. So that's why first rule is to be as good as possible and competitive as possible. And second is having network and relations with people that they know you. And then third is, make a choice and have a lot of options. I tell my guys, don't focus on one place. Have many options, then optimize after you have the options. Of course, first you need to create the options, get the options, and then decide. That's the best way to eventually find your dream position. And then don't forget, we change, and every time dream positions will change. And then eventually, you will adapt and see what is next better. So also don't forget, we have all these stages in our careers. If you look at my career, I've been in so many different continents, different stages, and it's been tiring, but eventually it had many advantages of, different phases you have. Again, as I said, different phases, different places are more optimal. So that's why, be dynamic, be open-minded, and create these great options, and then choose the best one in your given time of the career and life, and then move on.
Okay, that's really good answer. Yeah, actually, I think in China we have one old words is don't hire, don't die in one tree. Yeah, that means you need move. Yeah, you learn from different place, different cultures, different peoples. You have something to gain, and then you have something to pay, right? Yeah, no pay, no gain. Yeah. Sure. So, Professor Jagdish, did you want to comment on this? You're also moving the whole world. You collaborated with the whole world. Yeah.
Yeah, absolutely. It's that open-mindedness and also willing to really work with people. Basically, human beings are the same. If you're open-minded and you're generous to others, everybody wants to work with you, and they also want to be generous with you as well. So that's what I found by having worked with 30-plus countries, people from 30-plus countries. And so again, pleasure of giving is much more immense than pleasure of receiving. Whether it's with your students or postdocs or with your collaborators or anybody, if you really try to think about how can you help our students or postdocs or collaborators, they will exactly think in the same way. It's a mutually beneficial thing, even if you may not think about it. That's what it leads to. That's why you can create a good environment and also work with people from various parts of the world. And in fact, I've got a question for Metin. Metin, now you're working with people from biology and computer science, and of course in medicine and all. Of course, the cultures are different in different disciplines, because the biologists, the way they think and they work is quite different, and medical scientists work differently, engineers work differently, and chemists and physicists work differently. So how you're managing these different cultures and how you're able to really work with these multiple people from multiple disciplines?
Yeah, that's a great point. Like in the case of being in different countries, this is the same thing, that working with very different people is a great advantage, but also a great challenge, because each of them have different cultures of communication, thinking style, the scientific methods and styles. So maybe the answer is similar. First, be open-minded. So if someone is very, again, close to their own discipline and doesn't want to communicate with others, those people will be less successful. Because these days, most of the top research is very interdisciplinary. That means you need to work with different people in different disciplines. That means first you need to be able to communicate with them. And to communicate with them, you need to also understand how they think and also learn. I mean, I'm now learning medicine, I'm learning biology. You need to really learn also at some level. Of course, you need to have your own depth of specialty, but then try to learn different disciplines so you can talk with them and understand what they say. So yeah, I mean, those are things from your personal side. And then second thing is choose the right people with open-minded, because also if you get a biologist who is very also conservative, it's very hard to work with also from whatever you try. Or medical doctors are the hardest people in the world, because they don't have time for you. They have different thoughts. I mean, everybody has different, and that's why, as the other point, besides open-minded, work hard, persistence. I think the key word is persistence. Really keep trying. Again, if you learn and be open-minded, and hopefully if you don't hit to the wrong person, by just keep trying, eventually it works, but it takes time. All of these communications is years of communication and discussion and everything. But at the end, yeah, I mean, with the right processes and right people, it works out. But as you say, in the same lab meeting, someone talking about biological cells and someone talking about nanomaterials, and how to make sure that those people think that they are doing the same thing and they're going for the same mission is a lot of work. So I need to always go ahead and explain, look, because sometimes they think, I don't care about an MRI imaging methodology or someone. So you need to explain them that indeed the big vision, there is something combining them. So that's why you need to always keep reminding the people this interdisciplinary big goals, so that all different people don't think that they are fully disconnected with the others. So you need to connect them and merge them when needed. Those are things, need a lot of energy and effort. But at the end, if it works out, that can take you really to the next level because of research requiring that these days. And the nice thing about Max Planck is, because I can have many postdocs, also having expert postdoc level different disciplines is very important. If you have these as PhD students, you are doomed, because then you need to have a thesis in all different topics. It's not really possible to manage. But if you have these postdocs, they bring their expertise and you work with them, and that way you go really advanced level interdisciplinary fields and have biological data in the best way, material science in the best way, and robotics in the best way. That's why interdisciplinary research with the experts is really essential for very advanced research.
Yes, your question, I think, is we're going to go to Songyu. Yeah, Songyu, you will start your postdoc. Yeah, in the time period. Okay. How did you think about that? Yeah, give you last chance for the questions.
Okay, so the next is about the research-wise. We know your group did a very excellent job in the microrobot or bio-inspired field. And you also mentioned that they are promising in the clinical field, but we know that the needs of the clinical fields are typically different with the lab level stage. So can you give some opinions about the personal advice about how to find the key point and balance between the paper and the product? Thank you.
Product in the sense of commercialization, you mean?
Yeah. You also found some companies to commercialize your lab product.
Yeah, I mean, again, every country and every culture is different. America,
Okay.
it's a great thing to have a startup. I mean, in US, every professor who is really top is also even expected as a natural byproduct of research is to have startups. So that's why, indeed, it's very positive to do that. In Europe, sometimes it's tricky because every culture, every institution is a little bit different. But I would say, especially until tenure for junior faculty, top priority should be research and papers and productivity in science and research. So after you establish yourself and your tenure, then you can consider these options of having startup. And there you still need to be careful. Of course, that's why, I mean, a lot of publications, but also a lot of patents, because don't forget that top patents and technologies also come out of top papers. You cannot just have a commercialization, just sitting down and commercializing the lab. That's typically very correlated in top research or advanced research. So that's why I would suggest, keep doing high impact research and then patenting them, and then eventually at the right time, with the right students and the people, then commercialize it. And when you get to that stage, the danger or the risk is, or complexity is, make sure that it's very separated at some point. Some people are trying to do it together, then there's a lot of conflict of interest issues, ethical issues. I cannot ask my students to do research on the interests of the company. So that's why when the right time comes, structure it in the best way to separate from the lab. Of course, you can still license everything to the company, but make sure that they are well separated so that your interest in company versus in your own group shouldn't mix up. So yeah, I mean, if you balance those things, I think it's a great reward to have a successful startup. I would say I have one and I am now planning several. The big reward of the startup is to really see some advanced research you develop comes into reality in and used in practical daily life. I mean, I have my sunglasses with our gecko adhesive. I'm so happy to use it because it works great, and something we did 20 years ago or 15 years ago as a research is now used in the product. I think that's a great satisfaction of seeing what you do is really useful at the end. So that's why, I mean, it's worth it with the right preparation and right style.
Okay, cool. It's almost time. Professor Jagdish, did you ask other questions? Any further questions?
No, I think it's about time, and then only I think, Metin, the only question which I have is that as you know that the US is very much into entrepreneurship culture, and Europe and Asia, relatively speaking, they have the ambition to have the entrepreneurship culture, but also there's always a concern about the failure is seen as not desirable. How do you really manage that cultural thing and also try to really create entrepreneurship culture?
Yeah, especially Germany, you should see, it's the worst. I mean, people hate failure in the culture. People would go for the safe job rather than highly paid job. So it's a very interesting thing. As you say, coming from US to Europe after such experience, as we say, like, you need to spend a lot of energy and time to make it happen here. So that's the problem. Maybe China is a little bit different, and Japan may be similar in some sense. So that's why, as you say, I think as academic leaders, we need to also change the mindset of the people and explain them, look, only high achievements come with high risk, and not everything you do can be successful. We learn from the failures. So yeah, I mean, that's again, is easy to say, but to implement it, it needs a lot of effort for both us, but plus government policies and support. So that's why if you look at US, the environment is very supportive from not only universities, but also from agencies and many different aspects. So I think if these European and Asian countries do that in both high level, but also in the low level, encourage people to take high risk and possibly fail even, then I think then a startup culture will be established better. But on the other hand, Germany has a really great startup. So still, again, they do it, but they don't get to the. All Asia, they have the potential. That the tough thing is really we should use this potential of a lot of great ideas and developments turn into startups, which US does greatly. And I think by time, with the right policies and the changes in the culture, it will happen around the world more and more.
Okay, yeah, this question is, I have to add in some words here because we have many audience with in China, in mainland China. You're exactly right. The more risk, you have to take risk, right? Then you can, achieve higher. But in China, I know many people, it's very hesitate to take risk, especially the parents. They want their child to be more safely, to have a good position. To this, never take the risk. Never take risk, never win, right? The people who win the big future is they take the risk when they are young. Yeah, so be brave to take some risk. Be brave to be challenger. Yeah, to challenge everything. Yeah, if you challenge everything, then you get your chance, to win a big future. I think that's exactly right. Thank you so much. Thank you, three of you, join all this wonderful talk. And
Thank you very
the
much.
Soft robots, yeah, it's very nice. We hope to have you in China in the near future. Yeah. Okay.
Thank you very much.
Good.
Thank you, Alice.
Yeah.
Thanks,
That's
Metin,
the
for a great talk.
certification for you.
Thank you.
Matty, I hope I can give you next time when I met you.
Sure, great. Good night, Jagadish, and thanks everyone. Bye-bye.
Okay,
Take care.
thank you. Yeah.
Bye-bye.
At the end of today, so yeah, I want to show everyone that last year, yeah, exactly the same time, my mother state is like this. So we start the ICANX, and now the ICANX is transformer to be really a fantastic, platform for everything. So 1 year celebration is tomorrow. So we're going to have one new story come out. It's a science story named 科学派. So tomorrow morning at 10 o'clock. So please join us on ICANX. Professor Nin Yi was from Caltech, going to tell us a story for pi. He's a mathematics professor, so he's going to talk the stories about where and how and what pi can help us. So please join us with this fun, Chinese talk, the science talk. Tomorrow morning, 10 o'clock. Okay, see you. Yeah, next week we're going to have more, talks on site, and we're going to have different topics. Okay, yeah, it's a good time. Bye-bye, everyone. Okay.